In this video, we're going to talk about types of chemical reactions. So there's three different types that we're going to specifically talk about. Of course, these are not the only three types of chemical reactions, but these are the main three that we're going to focus on. So the three that we're going to talk about are acid-base neutralization, precipitation reactions, and oxidation-reduction reactions. In an acid-base reaction, we typically have an acid and a base that react to form a salt, some type of salt plus water. In a precipitation reaction, we mix two solutions and one of our product is a solid. In an oxidation-reduction reaction, we focus on the transfer of electrons. So we're going to go into more detail on each of these three types of reactions. So we'll start by talking about acid-base reactions. And to do that, we have to define what an acid and a base are. So there's a couple of different definitions that we commonly use for acids and bases. The first one is the Arrhenius definition. So this is named for Arrhenius because he was the one who identified the bases for conductivity in solutions. And he's also the one who came up with the idea that the extent to which a solution can conduct an electric current depends on the number of ions present. So we'll talk more about conductivity in another video, but he's also known for his definition of acids and bases. So the Arrhenius definition of an acid is that an acid is something that produces H plus in solution. And bases, according to the Arrhenius definition, produce OH negative in solution. Now, this is true of a lot of acids and bases, these definitions here, but there's one small problem with it. And the problem with that is that NH3, which is the chemical formula for ammonia, ammonia is a base, but it doesn't produce hydroxide ions in solution. So the Arrhenius definition doesn't really explain how something like ammonia can be a base, but not produce hydroxide ions in solution, and the OH here is the hydroxide ion. The definition that we more commonly use, at least in general chemistry, is the Bronsted-Lowry definition. So the Bronsted-Lowry definition still has acids as proton donors. They give up an H+, which if you think about a hydrogen ion, it has one proton and one electron. So if it's lost its one electron to have a positive charge, all that's really left is a proton. So we refer to H+ as a proton. So according to the Bronsted-Lowry definition, an acid is a proton donor, and a base is a proton acceptor. If we look at the example shown down here in this reaction, we have hydrochloric acid and water reacting. Hydrochloric acid gives up its proton to water, making it the proton donor and water the proton acceptor. So we get H3O+, which comes from the water accepting that proton, and Cl negative, which comes from the HCl giving up its proton. Now, we typically talk about, or we talk about a lot of times when we talk about acids, that they give up a proton. But when you see the products, most of the time you'll see that we write H3O+. The reason for that is that H+ ions don't exist by themselves in solution. H+ ions are very reactive and they tend to associate with water molecules, so we actually get our hydronium ions, which is the H3O+ that you see here. Now when we talk about acids and bases, We can further classify acids and bases as being either strong or weak. A strong acid or a strong base dissociates completely in aqueous solution. So for example, if we have something like sulfuric acid, this dissociates nearly completely into H plus ions, which is really H3O plus ions, and HSO4 minus ions. A weak acid or base will only partially dissociate in an aqueous solution. So the way that you can tell looking at the reaction whether something dissociates completely or only partially is to look at the arrows. Something that goes nearly to completion will have these full arrows, like this reaction up here. Something that dissociates only partially will have the arrows going in either direction, showing that this reaction is reversible. We can go from reactants to products or products to reactants, and you will have some concentration of the HSO4 minus ions and some concentration of the H plus and SO4 minus ions. So the key difference here is that strong acids and bases dissociate completely, whereas weak acids and bases only partially dissociate. So these are the 6 strong acids that we most commonly deal with in general chemistry. So these you will need to memorize. You will need to recognize these 6 as being your strong acids. So hydrobromic acid, hydrochloric acid, hydriodic acid, nitric acid, perchloric acid, and sulfuric acid are all 6 strong acids. If we look at a weak acid, if we could see this on a molecular level, if you look at the model here, we've got some models of acetic acid. So these structures like this are whole molecules. These are not dissociated. And then we have this one molecule here that's lost its H plus ion, and then we have the acetate ion left over. But all of the rest of these are undissociated acetic acid molecules. If we were looking at something like hydrochloric acid, we would have a bunch of H plus and Cl minus ions throughout our solution, and we would have very few HCl ions left. So you wouldn't see very many of any HCl molecules, but you would see the undissociated H plus and Cl minus if we could see this on a molecular level. Whereas with a weak acid, you see a lot of undissociated molecules and only a very few molecules that are broken apart into ions. The strong bases that you will need to be familiar with at this point. Anything that is a hydroxide of group 1A or 2A metals is a strong base. So things like sodium hydroxide, magnesium hydroxide, potassium hydroxide, calcium hydroxide, and so on. Those are all strong bases. They dissociate nearly completely into the metal and the hydroxide ion when they are in solution. Anything that is not a hydroxide of group 1A or group 2A, at this point you can assume is a weak base. One weak base that I would expect you to be familiar with is ammonia, or NH3. That one is a fairly weak base. As you can see here, the reaction is reversible. We have NH3 in water, you get some NH4 positive and OH negative ions. but you will still see a fairly decent concentration of the ammonia ions in solution. Now, you might have noticed, if you looked at one of the earlier reactions, that we had water acting as a base. If we look at this reaction here with ammonia, ammonia is the base. Therefore, water in this case has to be acting as the acid. So we have one case here where water acts as the base, and another where water acts as the acid. So the question is, what is water, an acid or a base? Well, the answer is that it can act as either, depending on what it's reacting with. So anything that can act as either an acid or a base, depending on what it's reacting with in solution, we call that amphiprotic. It can act as either one. It can act as an acid sometimes. It can act as a base sometimes, meaning it can give up a proton sometimes, and sometimes it takes one, just depending on what it's reacting with. It can play either role. So when we have an acid-base reaction, the acid and the base react to form a salt plus water. So we call this an acid-base neutralization. The salt comes from the cation of the base and the anion of the acid. So sometimes it can be something like this reaction, where we have hydrochloric acid and sodium hydroxide. We get NaCl, which we probably recognize as table salt, and water. But this is not the only example of a salt. Anything that is the cation from a base plus the anion from an acid is a salt. So anytime we react an acid and a base, one of our products will be water. The other is an example of salt. So let's take a look at a couple of examples here. So if I look at the first reaction here, if I take the hydrogen from H2SO4 and the OH from lithium hydroxide, that gives me my water. And then I have to figure out what my other product should be. So I have lithium left over, and I actually have HSO4 minus left over, because I only take one hydrogen to form the water. So my salt would be lithium bisulfate. Now let's take a look at the other example. If I take the hydrogen from nitric acid and the OH from calcium hydroxide, I get water. And then I have calcium and the nitrate from nitric acid. Now, if I just write CaNO3 here, I'm not quite finished yet. Because if you remember your polyatomic ions, nitrate has a negative charge on it. But if you look at the periodic table, calcium is in group 2, so it has a 2 positive charge on it. So CaNO3 would not be neutral. To make this a neutral compound, I need 2 nitrates to go with that calcium. So when you write these reactions, don't just take your water and then take your other ions and copy those over. Make sure that your formula is the correct formula for that compound. Sometimes you have to correct the formula to make sure that you have an overall neutral compound. The second thing that we need to do is we need to balance this reaction. So we got lucky the first time everything was balanced, and if you want to see this balance, you can go through and make your table and count everything up. Let's take a look at the second one. And the hydroxyl ion splits up, so I'm going to balance that separately. So if I count this up, I have 1, and then there's 2 hydrogens over here, so a total of 3. I have 1 nitrate, 1 calcium, and 2 oxygens. If I go over to the product side, I have 2 hydrogens, 1 oxygen, 2 nitrates, and 1 calcium. So I need to balance the hydrogen and the oxygen. So if I put a 2 here, that gives me 4 hydrogens and 2 oxygens. And then I also need to balance the nitrate, so if I put a 2 here, that gives me 2 plus 2 is 4 hydrogens, and that gives me 2 nitrates. So now everything is balanced. Now, the other thing we need to talk about when we talk about dealing with equations is molecular versus ionic equations. So a molecular equation is what you're used to seeing. The reactants and products are written as undissociated molecules. So we write hydrochloric acid as a molecule, sodium hydroxide as a molecule, sodium chloride as a molecule, and water as a molecule. So this is a reaction that you see all the time. The overall ionic equation is where we distinguish between molecular and ionic species. We write the ionic species as their ions. So if we go back to this equation, everything that is in solution, we're going to write it as its ions. So for example, HCl, that's aqueous. So in solution, that would be H plus and Cl minus ions. Sodium hydroxide is the same way. It's in solution, it's aqueous. So in solution, we would not see sodium hydroxide molecules. We would see sodium ions and hydroxide ions. Sodium chloride is aqueous, so what we would actually see is Na positive and Cl negative ions. And then I'm going to have to write water down the next line. Water is a liquid, so it would not break apart into its ions in solution. So we just write water. Okay, so this is what we just wrote out. In the net ionic equation, we remove all the spectator ions. A spectator ion is an ion that is present in the same form on the reactant side and the product side of the equation. So if we go back to our example here, we have H plus doesn't show up as H plus on the product side. Cl negative does show up as Cl negative. Sodium shows up as sodium. And hydroxide does not show up as hydroxide. So we get rid of all the spectator ions and we write just what is left. So I would have H plus. Now when I write the ionic equation, which was this here in red, I typically don't write the states there just because there's already a lot to write and it starts to get a little cluttered. But when you write the non-ionic equation, you do need to put the states back in. So you can keep them in this red equation if you want to. But if it helps you to make it a little less clutter, you can leave them out and then just put them back in when you write the net ionic equation. So our net ionic equation would be H plus aqueous plus OH negative aqueous gives us water, which is a liquid. So this is our net ionic equation. Okay, so that is all we're going to talk about for acid-base neutralization reactions. So now let's talk about precipitation reactions. Precipitation reactions are reactions where we mix two solutions and one of the products is a solid. And we can actually predict using solubility rules which of the products will be the solid product. Now I will give you a table of solubility rules in class. You do not have to memorize the solubility rules, you only have to be able to use them. Now with precipitation reactions, we can also write ionic and non-ionic equations. So here's an example of a precipitation reaction. Now we've kind of made this obvious which one is the solid because we put it in a different color. So all of the rest of the compounds in this reaction are soluble except for lead iodide. So if we're going to write a ionic equation, we would have, so nitrate has a negative charge and there are two of them, which means the lead has to have a 2 positive charge on it. And you do need to write the correct charges when you write ionic equations. So there are 2 nitrates, so that's where you get the subscript 2 here. When we write that in the ionic form, we put the 2 in front to show that there are 2 nitrate ions. Now this 2 in front of the potassium iodide applies to both the potassium and the iodine. So we have 2 potassium and 2 iodines. And that gives us, this 2 again applies to the potassium and to the nitrate. So we have and lead iodide is a solid, so we leave that written as lead iodide because it doesn't break apart in solution. Now if we're going to boil this down to the net ionic equation, we can cancel out the nitrates because they show up on both sides, and we can cancel out the potassiums because they show up on both sides, and we're left with P being 2 positive, which is in solution, PB. So that would be our net ionic equation. That's what's left over after we get rid of the spectator ions. So this is what we just did. This is the net ionic equation we came up with. We get rid of all the spectator ions, and we have the net ionic equation. So here's a few examples here, and we will go over some more of these in class. So you can go through these and write out what you think the ionic and non-ionic equations would be, and then we will look at more examples of this in class. Now, when we write a precipitation reaction, we can actually predict what the products are. If we take our two generic compounds, AB and CD, what would happen is that these essentially just swap partners. A goes with D and C goes with B, so we get AD and CB as our products. If either one of those are insoluble, a precipitate is going to form. So let's look at an example here. We have barium chloride and sodium sulfate. So again, these are just going to swap partners. So barium and sulfate are going to form a compound. And when you write these, you want to make sure that the formulas you write are correct. Just don't copy the ions over. Barium is in group 2. It has a 2 positive charge on it. Sulfate is one of our polyatomic ions. It has a 2 negative charge. 2 positive and 2 negative add up to 0. So this is the correct formula for barium sulfate. Now when sodium chloride goes together, we do not write. That is not a correct formula. Sodium has a positive charge on it, chlorine has a negative charge on it. So the formula for sodium chloride is NaCl. The way that we fix the fact that there's only 1 sodium and 1 chlorine on the product side and 2 of each on the reactant side is that we balance the equation by putting a 2 in front. So write your formulas, make sure that the formulas are the correct formulas for that compound, and then balance your equation. Now, once we do that, we can figure out which one of these is soluble and which one is not. Now, one of these is probably going to stand out as being soluble. Sodium chloride is just table salt. If you put table salt in water, what happens? Do you see a bunch of salt laying at the bottom of your glass? No. So we know that sodium chloride would be aqueous, and you can look at your table of solubility rules to see that. Barium sulfate is one of the ones we mentioned earlier as commonly being insoluble, so we put an S down here for solid. So don't confuse solid and soluble. The subscripts are for what state these are in, not whether they're soluble or not. So S is a solid, L is a liquid, G is a gas, AQ is aqueous. So if something is soluble, that means it's going to be dissolved in solution, which means it's going to be aqueous. If something is insoluble, that means it's going to be a solid. So now that we've labeled these, now we can write the ionic and non-ionic equations. So I'll go ahead and tell you these are both aqueous. And you could look these up on a solubility table. But for this reaction to happen, these would both have to be aqueous. So our ionic equation would be and barium sulfate is a solid, so we leave it together. And then we can cancel out the things that show up on both sides. So we're left with as our net ionic equation. The last type of reaction we need to talk about is an oxidation-reduction reaction. So oxidation-reduction reactions also sometimes get called redox reactions. So in a redox reaction, we have the transfer of one or more electrons. One example of this is a combustion reaction, where we burn things. Once we talk about how to label oxidation-reduction reactions, we can come back and see how this is an oxidation-reduction reaction. Another example of an oxidation-reduction reaction is when we have solid sodium metal react with chlorine to form sodium chloride. So if these are elements by themselves, these would be neutral. And we know from the periodic table, chlorine has a negative charge and sodium has a positive charge. So we had to have transferred electrons at some point in order to get a charge on these. So when we talk about assigning oxidation states, and we have to assign oxidation states to see whether we have an oxidation-reduction reaction. For an atom that's in a covalent compound, the oxidation state refers to the charge that atoms would have if those shared electrons were equally divided between the atoms that are bonded to each other. So when we do this in compounds that have different elements, for example, something like CH4 or Cl2O7, we give the electrons to the one that has the greater electron affinity, and we take the electrons away from the one that has less electron affinity. In an ionic compound, we assign the oxidation states based on what their charges would be on the periodic table. For something that's a neutral compound, the oxidation states have to add up to 0. And if they are an ion, the oxidation states has to equal the charge of the ion. So a few rules for assigning oxidation states. If you have just an element by itself, the oxidation state is 0. If you have a monatomic ion like sodium or chlorine, the charge is the charge on the ion. Fluorine is usually -1 in all of its compounds. Oxygen is also usually -2, which is what its charge should be according to the periodic table. The only exception to that is when you have a peroxide. So a peroxide is something like, that's hydrogen peroxide, which is one that you're probably familiar with because it's something we use quite frequently as a first aid in our first aid kits. Another example would be sodium peroxide. Hydrogen typically has a +1 charge in covalent compounds. So one thing I want to be clear about here, oxidation state is not the same thing as charge. We tend to use them interchangeably, but they're not really the same thing. A charge is an actual giving up or taking of electrons. An oxidation state is a charge that we've assigned to a compound. So sometimes it's almost like an imaginary charge. The compounds or the elements don't actually have those charges. We just assign them that for the purposes of determining oxidation and reduction. So don't confuse oxidation state and charge. They're not exactly the same thing. Let's take a look at a few examples here. We have CO2. So we said a few slides ago that oxygen has a 2 negative charge unless it's a peroxide. And CO2 is not a peroxide. So CO2, oxygen's got a 2 negative, and there's 2 oxygens, which means that the charge on carbon has to be 4 positive to make this a neutral compound. If we take NO3 negative, again, we know oxygen has to have a 2 negative charge on it. And there are 3 of them, which is a total of 6 negative. But we want this compound to have a negative charge on it, which means that nitrogen can only have a 5 positive charge. So 5 positive plus 6 negative will give us an overall 1 negative charge, which is what our compound has. So when we assign oxidation and reduction in a reaction, an oxidation-reduction reaction is characterized by transfer of electrons. So an oxidation is defined as a loss of electrons. So we increase the oxidation state by losing electrons. So the oxidizing agent is the one that accepts electrons. Reduction is characterized by a gain of electrons, so we decrease the oxidation state. A lot of times students are confused as to why we call gain of electron reduction, but what we're actually reducing is the oxidation state. So we gain electrons, but we reduce the oxidation state. The reducing agent is the one that is an electron donor. So let's take a look at an example here. We have metallurgy as the process of producing a metal from its ore. That almost always involves an oxidation-reduction reaction. So we are going to look at the conversion of lead sulfate to lead oxide, which is the first step in getting lead. So if we look at this reaction here, so we can't assign a charge to a transition metal because those can have different charges. So we have to start with the anion to figure out what the charge is on the transition metal. Sulfur is in group 6A or group 16, so it has a 2 negative charge, which would mean the charge on lead has to be a 2 positive. Oxygen is an element by itself, so it would have a charge of 0. If we go over to the product side, oxygen has a charge of 2 negative, which means this lead also has to have a charge of 2 positive. Again, oxygen has a charge of 2 negative, so 2 negative times 2 is 4 negative, which means that sulfur has to have a 4 positive charge on it. So lead does not change oxidation states going from the product to the from the reactant to the product. However, sulfur does. Sulfur goes from a 2 negative to a 4 positive, and oxygen goes from neutral to 2 negative. So if we look at sulfur, sulfur went from 2 negative to 4 positive, which means that it lost electrons. So losing electrons is oxidation. Oxygen went from a neutral to a 2 negative, so it gained electrons, which means that that is reduction. So a couple ways that you can remember these if you like little mnemonics, is one of them is Leo says grr. So Leo is loss of electrons. Is oxidation. So that's where we get Leo. And grr is gain of electrons. Is reduction. So that's where grr comes from. Another one that we use sometimes is oil rig, which is oxidation is loss, reduction is gain. So those are a couple of mnemonics you can use to help you remember the definitions for oxidation and reduction. So we are going to stop here and we will get some more practice with all of these types of reactions in class.